Welcome back to another additive manufacturing class. Today we're going to continue along our theme of design for additive manufacturing and start talking a little bit about CAD and computer aided engineering for additive manufacturing. All right, mostly today I want to talk a little bit about STL files, um, what they look like, how they're created, what can go wrong with them, and also what types of new file formats there are for STL. So we'll become a little bit more familiar with that. So there are several CAE or paths to a product, to an additively manufactured product. So one path is we start with a concept. This is sort of our traditional path. We CAD it, and then we fabricate it on our additive manufacturing machine. Another path is that we start with a concept, and so that's really our traditional path there in brown. Another path is that we start with a concept, we develop a physical prototype of it. So that could be an example. Maybe we carve it in foam, wood, clay, we mold it or sculpt it in clay. Maybe we have something around us that we want to start with, an existing part, for example, that we want to fit something onto, maybe a replacement part. We scan that part. From there, we create an STL file, and then we print it. Another part that's often important for medical applications is we start with an organic part. And so this could be an organ, a bone, some surface of the body, for example, a residual limb. And from there, we look at medical imaging. So that could be like an MRI or a CT scan. And from there, then we try to convert that into something that we can additively manufacture. All right, so we're going to talk a little bit first of all about this route over here on the left, which is just concept to CAD to STL file to print. And then at the end, we'll talk a little bit more about some of the difficulties encountered in scanning parts and what software is available for helping us with all of these. All right, so let's look at this concept to CAD to STL. And here's an example of a part from a project from a few years ago. And you can see this is an incredibly complicated STL file. It had several errors in it. And so we're going to look at some of the common types of errors that arise in STL files, and what they mean when you see them. And we'll also talk a little bit about some software for catching those errors and highlighting them for you. But first, let's talk a little bit about the STL file itself, right? So many of you may already be familiar with this if you've tried to 3D print something in the past, but all popular CAD software exports files as STL files. You can go from SolidWorks, you can go from Fusion 360, you can go from Siemens NX, you can even go Google SketchUp. All those types of software will allow you to store your drawing, your three-dimensional part in their native CAD file formats and then export it as an STL file. So the way I like to think of STL files is they're sort of the PDF of the geometry world or the manufacturing world, in the sense that you know, you could be using all sorts of different types of computer software and export what you're doing as a PDF file. It could be an image, it could be a Word document, it could be a PowerPoint document, an Excel file. If you store it as a PDF, almost anyone can view it regardless of what type of software they have on their machine. PDFs are fairly universal. But it does have some implications for us. So typically once we export a file as an STL file, it becomes somewhat difficult for us to modify it. So usually most of the modification we do is in the original CAD software, because that CAD software will allow us to make changes to the surfaces, make changes to the three-dimensional geometry. We've got a cube and we want to place a hole in it, or add lattice structures. It's usually much easier to do that in the native CAD software than it is to do that with the STL file. There are some exceptions and some software that allow you to modify STL files, but in general, we usually try to create our geometry in the native CAD software because it's really made for that. So when we convert to an STL file, there are a couple of things we need to pay attention to. One is the resolution, and we'll talk a little bit about that later on. And then the other is to make sure there aren't any errors in your parts as well. But first, let's look and see what a STL file looks like, right? So this is a snippet from an STL file for a cube, for a simple cube. And so typically if you have an STL file, you'll start with maybe the name of the solid up here, and then you'll break that solid apart into a series of triangles, right? If you have a curvaceous surface or a really complicated part, there could be thousands, tens of thousands, or even hundreds of thousands of triangles that are used to represent it. And those triangles then are represented very simply with 3 vertices, you can see them right here, and an outward normal, a normal vector, which tells you what is the outside of the part versus what is the inside of the part. So we've talked about this before, but let's suppose, for example, that we wanted to build a cube, right? And if this is the part of the cube that we can see, right? Then in order to build a cube and represent it as triangles, you would take each of these faces, right, and break them up into triangles. And so if we wanted to build a full cube with 6 faces, and each face is represented by 2 triangles, we would have 12 triangles to represent a cube, right? So let's take a look at this STL file and see how it has represented a few of the faces of a cube, right? So I'm going to draw a basic cube here. Okay. And then down here, what I'm going to do is I'm going to draw the axes X, Y, and Z, right? And let's see how it's represented some of these triangles, right? So the first triangle over here, let's look at it. All right, you can see it's facet normal, and that normal is in the minus Y direction. So most likely it's going to be a triangle on the front face, right, of this cube, the face that's closest to us, because that normal is going to be pointing outward, right, not into the substance of the cube, but outward into empty space. And then we've got 3 vertices. So let's draw these out here. The first one is at 0, 0, 0. All right. The second one is at 1 in X, 0 in Y, and 0 in Z. So that would be this one. The third one is 0, 0, 1. So that would be 0 in X, 0 in Y, and 1 in Z. So here we've got the vertices, right, of this triangle. So 0, 0, 0, 1, 0, 0, and 0, 0, 1, right? And so if this triangle is going to represent half of the front face of this cube. And then we have an outward normal, a facet normal up here that points in the minus Y direction, right? So that's the normal that comes out of this triangle that points in this direction, all right? Now let's look at the next triangle and see if we can decipher that, right? So it's got a vertex at 0, 0, 0 as well. It's also got one at 0, 1, 0, which would be actually here in the back of this cube. And then we've also got a vertex at 1, 0, 0. So that would be up here again. So in this case, if we draw another, just draw another cube here to make it a little bit easier to see. Right, we've got a vertex here at 0, 0, 0, another one at 0, 1, 0, right? So 0 in X, 1 in Y, 0 in Z. And then another one at 1 in Z, but 0 in X and 0 in Y. So that would be up here, right? So we've basically got a triangle that's back here on this left side of this cube, right? This triangle is right back here. So this is our triangle that we're drawing here, okay? And it's got a facet normal in the minus Z direction. Oops, looks like we might have made a mistake there, right? So let's see what we did to make a mistake there. We've got a facet in the minus Z direction, all right? So what we should have done there is we started out with a vertex at 0, 0, 0, 0, 1, 0, and then instead of going to Z here, that was a mistake, we should have gone over here. So let's try one more time, right? Okay, it's okay to make mistakes. We misinterpreted the axes, right? So let's draw an X through this and let's try one more time. See if you can find the mistake that I made. So in this particular case, we've got, because the facet normal didn't match up to the triangle, so we know we did something wrong. So let's try one more time. So we've got a vertex at 0, 0, 0. We've got another one at 0, 1, 0, which is 1 in the Y direction, right? Which would be back here. Okay? And then we've got another normal in at 1, 0, 0, which would be 1 in the X, 0 in the Y, and the Z. So that was our mistake. I put that normal up here where I shouldn't have. It should have been instead down here. All right. So this particular triangle here, if we draw the rest of the cube, is representing half of the bottom of our cube, right? And so then if we look at our facet normal up here, right, it's pointing in the minus Z direction, which means that the normal is pointing down, right? And that's correct because the normal should always be pointing outside of the solid, right? And so we could continue to trace out additional triangles and their facet normals, right? And so that's how we represent a part, right? We break it up into triangles. Each triangle has 3 vertices and a normal vector, which defines the outward direction away from the solid part. Now, why do you think it's important to represent a facet normal outward from the part? Right? Let's think about that for a second. Why would that be important? Right? So one of the keys here is that STL files represent only the surface of a part. Right? STL files don't represent the solids themselves per se, right? There aren't any 3-dimensional meshes, for example, made up of cubes or triangular prisms or other things like that that represent the solid meat of the part. You're only representing the surface. So having these outward normals helps the software understand what part is solid and what part is exterior to the part. So as a process planning software starts to interpret these STL files, then what will happen is that the process planning software will understand, okay, as I'm scanning, looking across this part bed, I see, okay, here I've intersected with a triangle. Now, am I supposed to start or stop laying down material, right? And so as I approach that triangle from the outside, I should be going against this facet normal, right? And then I'll see that I'm intersecting with a triangle. So I need to start laying down material until I intersect with another triangle. And then as I leave, I should be more or less parallel with a facet normal. So that's kind of how that deposition software thinks about that. So it's really important to have these normals because it helps define what's inside and outside of a part. Okay, so a couple of things to think about with STL files. One is that these STL files have a resolution. We have to think very carefully about that and how much resolution we want or need, and we'll talk about that in a second. The other is that STL files can have errors in them. And some of the common errors I've listed here, non-manifold or geometry that's not watertight. Okay, so it means it has holes in it or something else about the geometry is not right. And so then if it's not watertight, there's no clear definition of what should be solid or inside the part and what should be outside the part, not solid. It can also have some other errors, which we'll talk about in a little bit. There is some software for checking and repairing STL files, and I've listed a few of those down here. Okay, so NetFab Basic, I think they no longer call it Basic. There's a NetFab a Standard and a NetFab Premium. There's a free download for students because NetFab is now owned. It used to be its own company, and NetFab Basic was just free for everybody to download. Now NetFab is owned by Autodesk, and Autodesk is providing free software, including Fusion 360, to students and faculty and staff at educational institutions. So you can actually download NetFab for free, as long as you're still a student and use it for free. And so it will look for errors in your STL files and it will repair them. There's a couple of other pieces of software here too. Geomagic is really the industry standard for doing this. And they offer a free trial, but I don't think they allow you to save files. At least last time I checked, they didn't allow you to save anything that you've done in that. You can just play around with it. There's also a software called Minimagics, which is really free and very easy to download, and it checks for errors in your STL files, but it won't repair them. NetFab will. And then the last check we do on files is our SLS machine. When we build them there, it checks files for errors. And it will simulate the build and it will correct some of those errors and also help us see if we have errors that influence the build, right, that cause some sort of crash in the build. So when we build parts in SLS, we always do another check for that. All right, first let's look at resolution on STL files. Let's look at some STL files for realistic parts and look at resolution, and then we'll talk a little bit more about the errors. Okay, so one of the errors that can come up in STL files is just poor resolution. And so let's say we wanted to build this geometry with a hole through it. And you can see here that depending on what type of resolution we specify, the file can look very, very different. So remember, you're having to take all of these surfaces and represent them with triangles. All right, and if we look in the upper left, this is a file for which the resolution is quite coarse. And so you can actually see on this file some of the triangles, right, that have been represented. And I'm highlighting a few of them here with my pen so you can see them. And because of this coarse representation of the triangles, you can actually see that the hole doesn't look round anymore. It looks visibly polygonal, right? It looks like a polygon. And so if we try to print it, it will look like this as well. And you'll see what is clearly a linearized version of this curved surface that's supposed to take place inside. And then if we add more and more triangles, right, in the limit, we actually approximate a circle. And so you can see here on the right-hand side where the addition of lots and lots of triangles, you can see them in these fans here in the upper left and right and the bottom left and right of this particular part. You can see all the triangles that are inside that fan there, and that allows us to approximate this curved surface much more smoothly. And so one of the things we want to think about is that the higher the resolution of our STL file, the larger the file size. So to get this high res image over here in the upper right, we have to use lots and lots of triangles, whereas to get this low res geometry here in the upper left, it only takes a few triangles, right? So how is resolution really determined? Well, one of the primary way to measure it is in terms of error, right? And so here you can see a measurement called chord height, right? And what that really measures here is if we kind of zoom in on one of these areas here, you'll see you've got a curved surface and you've got a straight line that's representing it, right? You've got a curved surface and you've got a straight line from a triangle that's representing it. And the chord height here is just the difference or the error, the maximum error between the curved surface that you intend to build and this triangle, right, that's underneath it, that's approximating it, right? And so this is our chord height or our error, okay? So the larger you allow that chord height to be, the fewer triangles, the poorer the resolution, right? And so then you get a design something like this one. The smaller that you require that chord height to be, the more triangles you'll use, at least if it's a curved surface. The larger your file size, but the smaller the error, right? And so here are examples here of taking this basic part and changing the chord height. All right, so one of the things you want to keep in mind is that although the geometry over here in the far right for this super high res image looks fantastic, the geometry for the high res image in the middle looks quite good as well, and much better than the low res. There's no point in decreasing the chord height beyond the resolution of your machine, right? So here when we get to 0.001 inches, we're really already in the ballpark or even better than the minimum resolution of most of our additive manufacturing machines. So there's really no point in having a resolution any better than that. The price you pay if you go to a super high resolution, so again, this high resolution or this medium resolution in the middle, is already, the error is already on the sort of in the ballpark of or even smaller than the minimum feature size smaller than the minimum feature size that you can build on most of our additive manufacturing machines. So there's really no need to have that resolution much greater. If we go over to the super high res, right, you won't be able to see any difference between the super high res and the high res when you print it, because all those errors are smaller than the minimum feature size of the accuracy of the machine. And the price that you pay to go to the super high res is that then you won't be able to, your file sizes will be much, much larger, right? So again, once your chord height is small enough that it's sort of below what your machine can resolve, you're typically not going to get any more benefit out of decreasing that chord height even further. So here's just a simple part. You can see this looks like a curved pipe, or maybe this would be a flow channel inside of a three-dimensional part. And here what this particular author has done is converted that flow channel into an STL file. So up here we've got the CAD representation. Here we've got a low fidelity STL file. And you can see a 60 micron surface deviation, which is already quite good. That's 0.06 millimeters. So that's already really quite fine compared to what most of our additive manufacturing machines can fabricate. We've got, in this case, 1,000 facets and a file size of 51 kilobytes, right? Here, if we continue to lower that surface deviation, which is our chord height from the previous slide, to 9 microns, then we've got 6,000 facets and a file size of 320 kilobytes. All right, no problem, not so bad. Then if we go over here to the bottom right to a high fidelity STL, now the surface deviation is a micron, right? So we can barely even see the triangles that are representing this part. We've got 50,000 facets and a file size of 2.5 megabytes, and that's just for this channel. So imagine this channel were inside a more complicated parts with lots of other features. Then all of a sudden your file size is starting to really grow and to expand with almost non-linearly, right, with the fidelity of the file. So that's something we need to keep in mind, right? So again, once you have a surface deviation or a chord height that's much lower than what your machine can resolve, there's really not much use in going any smaller than that, because you'll just increase the file size and the part that you print will be indiscernible, right? So if we look at sort of the difference between these two parts, practically speaking, it's just that the one in the bottom right has a bigger file size, because when we print both of these, they'll look the same to us if we print them on the machines that are available to us, unless we had a really high resolution sort of micro additive manufacturing machine, right? So now let's talk a little bit about some of the errors that we can find in STL files. So one error that we can find is boundary edges. So each edge of a triangle in STL file should be connected to exactly 2 faces, right? So if we think about that for a second. If we think about our simple cube that we were going to fabricate with STL, if we break each face into triangles, right? Think about each triangle, right? Each triangle, the edge of each triangle is connected to exactly 2 faces, right? So if we look at this edge, for example, it's connected to this face and this face. If we look at this edge, for example, it's connected to this face and this face. So each edge should be connected to exactly 2 faces. If it's not, your part may not be watertight, right? So for example, look at the bunny down here in the bottom, and you can see some edges here that are highlighted in red. The reason is because those edges, they're on the bottom of the bunny, right? The bottom of the bunny is flat, but those edges are connected. They're edges and they're connected to only one face. So what you actually have on the bottom of that bunny are holes, right? So if that would be as if, for example, we took this, what if we took this cube, right? And we wanted to build it as a cube, but for some reason, the top of it didn't resolve and it didn't turn into triangles for us. Then what we'd find is each of these edges here along the top, this one, this one, this one, and this one, would be connected to only one face because there's no top face, right? They'd be connected only to the face that's underneath them, right? That's on the side, one of the sides of the cube. And so that's an indication to us that this part is not watertight. You intended to build a solid cube. There's no top face on it. So it's not going to resolve. The machine is not going to know that it's a solid part, right? And it's not going to be able to build it because it's not watertight, right? It's not fully enclosing that three-dimensional cubic solid that you wanted to build, right? So that's one problem, is a boundary edge. Here's another way to look at those. So here's a box here where the front face here, the one that's closest to us, is missing, right? So if your intention here on the top, right, let's look up here at the top, if your intention was to build a closed box, right, a three-dimensional box of material, the error here is the missing face, right, on the front. And that's another example of a boundary edge, or what we call a non-watertight, can also sometimes be called non-manifold. So that's a term that's borrowed from computational geometry, which means it's not watertight. All right, so the solution is that we need to add a face in CAD. And so that face has then been added over here, right? And so now we have a closed box. Every edge is connected to, as we break up this cube, right? And we convert it into triangles, right? Regardless of how we do it here with these triangles, right? Each edge is going to be connected to two faces, right? So we've solved that problem. Whereas before, if we look at an edge like this, let's say the top is broken up into triangles, this edge is connected to only one face. There's nothing down here. Now that edge is connected to two faces, and so we're in good shape. If your intention was to build an open box, right, like a cardboard box with an opening on the top, there's still a problem with this file, right? So let's look down here. The error is that you've got 2D surfaces with no thickness, right? You've built a surface that is infinitely thin. And so again, the machine can't build this because it needs finite thickness, right? Imagine a desktop FDM machine trying to build a box with an infinitely thin wall, right? Usually the process planning software just takes that feature completely out of the build, and it's not there at all. It either rounds it up or rounds it down, but if it's infinitely thin, it'll probably round it down and take it out altogether. And so the solution is to add thickness to these surfaces. So whereas here on the left-hand side, if you look at this surface, it's infinitely thin, it has no thickness. Here on the right, you can see all these surfaces now have thickness. So they are in fact three-dimensional solids. You've still got an opening in the front here, and that's fine, it's an open box, but these surfaces now have a finite thickness. And so then, provided that finite thickness is large enough to be resolved on your machine, you'll actually be able to build it. Okay. You can also get holes in other ways. So let's take a look here let's look at this part of the slide here in the bottom right. And you'll see you've got two surfaces. There's one surface and two surface. And then this is the boundary here. I'm just going to draw an arrow so as not to mess it up. This is the boundary between those two surfaces. It's curvaceous in 3 dimensions. So it's difficult for us to represent that boundary with triangles. All right, let's look at surface 1 and where it has placed its triangles. You can see those triangles, one of them here. And then let's look at surface 2 and where it has placed its triangles, right? You've got a triangle here adjacent. You've got a triangle here, right? And then what you've found is this green area in the middle is open. It's a hole, right? It's not being represented by a triangle. Right? And so what really needed to happen probably is that this triangle gets divided, right, into additional triangles, right, to accommodate that hole. That's really what needs to happen, and then that hole goes away. But that's not what happened in the original STL file. So if you have a hole, the machine can find it very difficult to build that. And as it's moving through, what it typically does is it'll move across and look at, as it's process planning, it'll move across the build envelope until it gets to a triangle and intersects with a triangle, and then it'll start building. And then as it goes through the part and exits the other side, it'll say, oh, okay, I've intersected with another boundary triangle, I need to stop, provided that the facet normals are oriented in the right direction, right, towards the exterior. But if it encounters a hole, it doesn't know to stop, right? And so what would happen, let's say you had, for example, something you were building, right, like this, right? And let's say there's a hole here, right, for some reason. what it would do is when it gets to that layer, as the machine starts going across, right, it'll start building, build, 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 build. Then it'll get here and it won't ever encounter a triangle or a surface that says stop building. So it'll continue building, like let's say it's an SLS machine, it'll just continue building off the side of the part and all the way to the end of the build chamber. And so that'll be a failed build because it won't obey the geometry that you really wanted it to build. So it relies on, as it process plans, as it scans across, okay, I've hit a surface, I see a triangle with an outward normal that's facing me, so I'm going to start building, I'm going to build, build, build until I get to another surface. Then I'm going to stop, another surface with an outward triangle that's sort of generally pointing in the direction that I want to go. And I'll stop, and then, I'll continue tracing additional paths through the part. But if there's a hole there, it doesn't know to stop, right? So there's some other things that can happen as well. You can have bad edges and bad faces. So here's a really good example of one. Let's look here, right? In this case, we've got a face that's inside of a cube. Here you can kind of see it, barely see it in there. And it shouldn't be there because you don't need a face inside. You only want faces on the exterior. Here we've got a case that could theoretically happen where you've got a side of a cube and it's broken it up into two triangles, one with this way and one with another axis this way. And so it's basically taken that side of the cube and it's broken it up into two triangles, 1, 2, but then it's also broken it up into two triangles this way, 3, 4, okay? And that's incorrect because these triangles are overlapping, right, and representing too many things. So those are a couple of examples of errors that you can get, right? There's also an example of something called an inverted normal. So remember how we talked about how as an additive manufacturing machine process plans, it's going to start scanning and it's going to look for a surface to start building, and then it's going to look for another surface to stop building, especially like an SLS machine. And it's going to look at those normals and it's going to want those normals to be pointing outward so it knows what's material and what's not. So in this case, if the normal of this particular face should be pointing outward, right? Orthogonal to that surface. If instead it's pointing inward, then that would be what's called an inverted normal. And what happens if you don't fix it? Again, the additive machine will start to scan the box, but it won't stop because it doesn't detect the boundary. It might think it's a box within a box for some reason, that was just an artifact, for example, of when you originally created the part. It's looking for an intersection with a triangular surface, a triangulated surface, and it's looking for that normal to be pointing generally in the direction in which it's scanning out of the part, right? Here are some examples of typical errors as well that you can see. So here are some holes. You can see here, this is not a watertight part. So you can see some holes here on the edge, so it won't be able to build that. Here's an example here. It looks like on the bottom left here of something that looks like it was meant to be a shell, but it's a surface and not a solid, so it can't actually print it because it doesn't have finite volume. It's infinitely thin. Here's an example here where we've got floating surfaces. You can kind of see the triangles here that aren't connected to anything else. And so that could lead to non-watertight parts or just disappearing features in your build, right? So those are all important things to think about, right? Okay, so let me just go back real quick and just draw your attention then back to the software that we talked about. When you generate an STL file, especially if it's a really complicated geometry, like if it has lattice structures in it, really complex form-fitting features, or if you've scanned something to use as input to your file, if you've got lots of internal cavities or holes, all sorts of things like that, the likelihood that you might have an error in your STL file goes up. CAD software has gotten better and better and better over the years in fixing these errors or not generating them in the first place. So about 10 or 15 years ago, when I started teaching the class, almost all the files the students generated had errors in them. The CAD software just wasn't capable of generating good watertight files all the time. And so we'd have to repair all of them. Now the frequency of repair has gone down. We don't have to repair them as much, but it's still have to do it sometimes, especially with really complex objects. So the best way to do it, Mini-Magics is a really cheap, free, inexpensive, fast, lightweight way to check for errors. And I use that a lot to just check for errors, but it won't fix the errors. So in order to fix them, you need to use something else. Like NetFab, for example, will fix things. So if it finds, Mini-Magic might tell you that you have inverted normals and non-watertight solids, or might tell you that you have shells, which is another word for those infinitely thin surfaces, but it won't fix them. Mini-Magics won't fix them. You have to go to something like NetFab to actually fix them. It'll fix your inverted normals. It'll patch your non-manifold or non-watertight surfaces, okay? All right, so let's talk a little bit about, so that was sort of the direct concept CAD to STL to additive part, assuming that you're drawing everything in CAD. Now let's think about some of the additional headaches that arise when you decide you want to 3D scan a part and then convert it to STL. All right, so this is a pretty common technique, particularly if you're doing things in industrial design where you might want to conduct interviews and maybe create prototypes out of clay or foam or other substances, Play-Doh, et cetera, that allow the customer to just kind of touch and feel the object, or maybe you want to form fit something to someone's hands using clay or Play-Doh, modeling clay. And then you'd like to 3D scan that object and convert it into a CAD and an STL file that you can then print. Right? So let's take a look then at some of the challenges that we sometimes face, right? So here's an example here. This is an example of a whiteboard marker. You can probably recognize it. And what I did was I put this whiteboard marker on a scanner. And this particular scanner has a plate that the whiteboard marker sits on. I'll help you visualize that. So it sits on a plate, and that plate rotates. And then off to the side, it has a laser scanner, all right? Okay, that laser scanner stays fixed, but it moves up and down, okay? And so you can kind of, and as it does that, it basically shines a laser light onto the object and looks at the time of flight. And based on that, it can tell how far away that geometry is. And it generates what's called a point cloud of data. So even though these look like lines, they're not actually lines. They are in fact points. And you can kind of see that over here if you look closely, that they're points and not lines. And so what it's done is it's rotated the pen, the whiteboard marker, around its axis on this plate. And this laser scanner has moved up and down to capture concentric images, right, capture surface images of this whiteboard marker as you move up, 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 sort of like a spiraling pattern, okay? So one of the things that you'll notice though with these scans, right, is that they're noisy, so they're not perfect. And so if you look down here, look at the side of the whiteboard marker here, and you can see, for example, that it's not perfectly smooth the way we would like. The other challenge we have with these whiteboard markers is that you can only see line of sight. So if we place this whiteboard marker on its rotating base and we scan up and down, one of the things we can't see is, this is a view of the tip. Up here is a view of the top of the whiteboard marker. It's not possible for the laser to see what's going on in here because it's only scanning it from the side. So if we then try to create an STL file from those points, the most straightforward way to do it is to take those points and to directly connect triangles to triangulate all those points. All right, and so if we try to do that, you'll see that all the noise that's in this data gets converted into erroneous or noisy STL files. And then other aspects of it that we can't see very well, like the top, It doesn't really get filled in at all. So here you can see, if we look closely, that there are lots and lots of areas here that aren't watertight, right? We've got a bunch of STL files, triangles here, STL triangles that are not connected to anything else. So they're edges with only one face. And we know what that means, right? That it's not watertight. So then this is a good visualization here of our whiteboard marker. All the noise that we had, right, from our scan, you can see it cropping up here and here. So it should be smooth, but it's not. And then you can look at the top here and you can see all these areas again that weren't watertight, right? Here's another example of a scan. So this is an example of a handle for a paintball gun. So in this case, what the students did was they created a clay model of this handle and then scanned it. And so you can see this STL file from the scan over here on the left. But the scan didn't pick up everything. There are some non-watertight portions here. Thankfully, it wasn't too noisy, but there are definitely some non-watertight portions here. And then if we go over here to the right, what they did was they basically took that scan into their CAD file, and then they used SolidWorks to then loft a surface that matched it as closely as they could. And that's how they created their solid model. But there are other ways to go about it. So if you find yourself with this type of noisy scan data, there are some good software options to help you clean it up and smooth it, because this is common. This happens all the time. All right. So software for STL files, right? There is software that will act on or manipulate STL files themselves, right? They'll convert point cloud data to an STL file, and they'll also help you manipulate an STL file, right? So typically something like SolidWorks doesn't like to manipulate solid STL files very much. It likes to manipulate files that are stored in its native format. So some different software options. There are commercial options for manipulating STL files and for easing this process of converting scanned point clouds to STL files. So Geomagic is really the industry standard, one of the industry favorites. It's very expensive though. And the free trial doesn't really give you much functionality to save parts. There's another software called Rhinoceros, which is really popular in architecture and some other fields. It smooths scan data and manipulates STL files, allows you to modify those STL files just like you would a solid part in, say, SolidWorks. SolidWorks also has some options as well. They're available as part of the premium version. But there's also some open source freeware that's available to manipulate STL files. So one is MeshLab. That's been around for a long time. It's very popular. It will help you convert scan data to STL and also manipulate STL files. And what I mean by manipulating an STL file is, let's suppose you have an STL file of a part. Let's say it's an animal, some sort of icon, and you wanted to maybe make that animal into a keychain holder. And so in order to do that, you needed to extrude a hole through it so that you could fit a keychain through it. And so Rhino or MeshLab, right, would allow you to take the STL file, add that hole, save the new STL file, and print it with the hole in it, right? There's another software called Cloud Compare that manipulates point cloud data. So one of the things it can do is remove outliers and noise. So that really, really noisy point cloud data that we had here from our whiteboard marker, Cloud Compare would allow you to eliminate a lot of that noise, all these noisy points we see out here that really shouldn't be here. It'll notice that because it'll notice that it's farther away from its neighboring points than it should be, and it'll smooth it. It'll bring it back to pull it back to the surface, so that then when you generate an STL file, it'll be nice and smooth, okay? So that's one of the things that does. And then of course, MeshLab will help you convert that scan data to an STL and also manipulate the STL file. So once you can manipulate the STL file, you can also do things like take another surface and use it to cut off all this noise. You could add surfaces inside the top of the pen here, right? And fill it in so that it's watertight. And so those types of operations are really important if you're going to move directly from scanned data to a file. You know, we're not on campus, so this doesn't have as much importance as it usually does. We have a very old scanner that operates in the same way that I mentioned for this whiteboard marker, where you can rotate the part and scan it as you go. But we don't have a new modern scanner. A FaroArm is a really good example of one. We're working on getting one, so hopefully subsequent students who can take the class will be able to access those. All right, so STL files, right? They represent the surface of a part with triangles, right? Let's go back and look at one of those just to remind ourselves again what we're talking about, right? So this was this example of taking this, this curvaceous surface, what looks like a channel or a tube, and representing it with triangles, right? There are quite a few drawbacks to STL files, right? Okay, and one of those drawbacks is that all it does is represent the surface. It's a pretty unintelligent representation of what we want to print. What about some of our new machines that can print in multiple materials? Can you think of one? The object that we talked about that can print in more than one material or even grade the material. This type of file representation doesn't say anything about that. What about a 3D printer, like a Z-Corp type machine that can print in color? This doesn't say anything about that. So it has several limitations, right? One is that they can't store material choice. So if you have more than one material or the ability to grade it, can't store that information. It can't store color. It can't store orientation or other build specific directions that you might want to embed in it. The other shortcoming of an STL file is that it relies on triangles, which scale poorly with size and complexity of the part, right? So we saw that earlier. And just to give you a data point, a 10 centimeter sphere with 10 micron resolution, which isn't outrageous, right? That seems reasonable. 20,000 triangles, every one represented with 3 vertices and an outward normal, right? So there is a need for a file format that will maybe give us a little bit of a better control and higher fidelity representation of our part. All right, so an AMF file format is an XML-based format that is an alternative to STL, right? So it's an alternative. It's been an ASTM standard since 2011. It's been a little slow to adopt, though. There are quite a few service bureaus will accept AMF files, but a lot of people are still working with STL. I think a lot of that is driven by the fact that a lot of parts are still built in a single material. So this need for a multi-material format hasn't quite gained traction yet until that happens, I think, at a wider scale. But an AMF file is an XML-based format. And so, you know, if you're not familiar with XML, don't worry about it. Basically, it allows you to identify objects, okay? Those are volumes, and you can use a polygon mesh to represent the volume where the polygons can be curved. So if you have, for example, you know, a spherical surface that you want to represent, instead of having to represent it with planar triangles, right, which are always flat, and you have to use a lot of those little planar triangles, you know, to represent it, you can instead represent it with curved triangles, right? And those triangles then have vertices, but they can also have outward normals at each vertex, and you can adjust those outward normals to change the curvature of the triangle. So then you can actually represent a curved surface on a sphere with curved triangles, which means you have fewer triangles. Even though each triangle now has 3 vertices and 3 unit normals, one at each vertex, instead of just 3 vertices and 1 unit normal for a planar triangle. So for a planar triangle, we've got 3 vertices and 1 outward normal. For a curved triangle, we've got 3 vertices and 3 outward normals, one at each triangle, one at each vertex, sorry. So it's a little bit more information, but that's well worth it because you could use far fewer triangles to represent something like a sphere, right? All right, you can also describe for each object different materials. There can be multiple materials, there can be mixed or graded materials. So an object, for example, will allow you to have a black flexible material, a white solid material, and then to grade between those two. lattice structures as well. You can define textures or colors for the surfaces if you want to have them be different colors. You can define what are called constellations, which are pretty cool because that's the pattern of objects within a file. So you can take multiple objects and locate them and orient them on the build platform. You can also add other metadata to the file, what copyright information, authorship, and other build instructions and things like that. So let's take a look at an AMF file and see what it looks like. So this is an AMF file for a pyramid, but the unique thing about this pyramid is it's going to be two materials, all right? So we're going to have one solid defined by, let's take a look at this description up here. We're going to take this object, this pyramid, and divide it into two different materials. So the hard material is going to be in a solid defined by vertices 0, 1, 2, 4, right? Those vertices, right? That solid that's sort of on the front left. And then the back right, the one defined by vertices 1, 2, 4, 3, 1, is going to be a soft material, right? Okay, so if we look at the AMF file, what we've got here is it starts out by defining units, right? Okay, so it's going to be in inches, which is something that STL files unfortunately often don't define. So you have to guess what the units are, whether it's inches or millimeters. And that can be a source of confusion. We're going to give it a name. It's a split pyramid, an author, John Smith, an object. So this is the first object, ID number 1. It has vertices. You can see the different vertices that are 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, and so on. All the different vertices, the locations of the 1, 2, 3, 4, 5 vertices that make up this pyramid, right? 0, 1, 2, 3, 4. Then what we've got is a volume. We've got two different materials we're going to define. One is a hard side, one is a soft side, right? And those are defined, the boundary of the hard side is represented by triangles. Triangle 210 is the bottom of the hard side. Triangle 014, 014 is the front face of the hard side. Triangle 412, 412 is sort of the back side of the hard side. Triangle 042 is the left side of the hard side, and that defines the hard side. And then we've got the soft side where triangle 231, right, is defining the bottom of it. Triangle 134, 134 is defining the right side. Triangle 432 is defining the back side. And then triangle 421 is sort of the front side of that soft side. We're giving each of those a material type. So down here, we're going to define material ID 2, which was the hard side up above. We're going to call it the hard material. And then material ID 3, which was the soft side up, we're going to give it a soft material. And in this case, they're providing colors, which is RGB, as well as in some cases an A as well, which is a transparency. So this will allow you, if you're assigning colors, to give it a particular color as well as a transparency. Right, so that gives you some sense here of what an AMF file will look like. Right? So it just gives you a lot more flexibility. It's especially useful if you've got curvaceous complex structures because it can lower the file size. It's also especially helpful if you're trying to do colors or multiple materials, and it accommodates all of those things. All right. Okay, so one of the things I encourage you to do, just to get used to this, is why don't you open up a computational geometry CAD software. Many of you have access to SolidWorks. If not, you can also use any other geometry software, you know, the equivalent of Google SketchUp, anything else you'd like to use to generate some geometry, and then try generating some STL files, right? And look and see what those triangles look like, and if you can figure out how those triangles correspond back to the part that you built. You could also, if you have, I know you're working from home on your personal laptops, but many of you are going to need CAD anyway to do your final project. So many of you probably have CAD, like SolidWorks, or you can log into SolidWorks, right, through school, and use it to generate some parts. So try to do that. Generate just some simple things. Maybe, a cube, a triangle, put a hole in the cube, put a circular hole in the cube. Look at the STL file, pull it up. You can pull it up as a text file, and you can look at the actual triangles that are representing your parts. So you'll see them all listed, and just take a look and play around with it a little bit, get a little bit of familiarity with the STL files, right? And if you do that and you take a couple of screenshots, shoot me an email to show me what you've done for an extra credit point on your exam, because I think it'll be interesting for you just to kind of play around and get a little bit familiar with what these STL files are and how they do. So again, pull up whatever CAD software you have access to, generate an STL file for a really simple part, then add a feature to it of some sort, generate another STL file, and kind of play around with that, and take some screenshots, write down a few sentences about what you observed in the STL file, and send it to me, and for a little bit of extra credit on your midterm exam. All right. Okay. Best of luck, and we'll see you next time. For our next lecture, we'll investigate a little bit of topology optimization, which is sort of our next step in customizing these files in CAD and CAE.